thanks, Kiara, for giving me the opportunity. This talk is going to be on digital twins in contact mechanics. It's actually mostly a project by my PhD student, Christian Müller, that I'm going to talk about. But some of the support for coding was also done by my PDF, Sergei Sukhomlinov, so they did the hard work. Let me start talking first a little bit about the classification of digital twins. Perhaps also in the context of contact mechanics. And what we always talk about is identical twins. This is typically aimed for, but almost never achieved. And what happens more often is that we have dizygotic twins, like here, the two Star Wars characters. And even that is difficult to achieve. And one of the examples I've been struggling with, and I've been asking questions to Daniele, is the problem of contact mechanics, of triboelectrification, when we have a simple, not simple, a complex system like an amber strip rubbing against a cat. And how can we achieve that when two surfaces touch, that basically the oxidation numbers of various atoms differ after the impact and before the impact. And I think that is one of the biggest challenges to come up with good digital twins. And Daniele did a very good job, and it's brave, but of course, this part of the digital twin is missing. So the usual way of modeling or creating digital twins is you first have reality, then you make some reasonable approximations. From that, you generate a mathematical model, which for people also working on continuum mechanics is often partial differential equations. And then in theory, or even in computing, we make reasonable approximations to find a solution. And this is basically what most simulators spend most of their time on. But the really difficult part often is to actually come up with a good model that we want to study. And I think this is where the big challenge lies. Now coming back to the classification of digital twins, what we always assume is that experiment is first, and typically the first identical twin is the stronger twin. And I think we simulators should be a bit more self-confident and say, why do we have to be second? We can also be the first twin. So why not create a digital twin first and then ask the experimentalist, here, go ahead, create that system. Perhaps we can learn something. And one such example, it dates back a few years, but I think it's worth mentioning here to set the stage. So the alternative would be to define a mathematical model and then to create a reality mimicking these models and perhaps use computer simulations to find the solution. So perhaps I should get a laser pointer, which is nicer. Okay, so one such example dates back a few years, where I was a bit tired of people claiming big things in contact mechanics. So I went ahead and defined properties of a contact with mathematical precision, including, for example, a surface topography, the surface energy that the two surfaces would gain when they come into contact, the range of adhesion, and so on and so forth. And what you see here is the digital twin, which was born first. And very much to my surprise, there was an experimental group led by Greg Sawyer in Florida, who said, well, we print this stuff and we do the inverse modeling. So they visualized the contact with total internal reflection. And what you see here is a comparison between what Greg's group believed to be the contact lines and between what we computed to be the gaps. So this is really basically a system that was meant to be 100 microns by 100 microns. Greg scaled it up to larger dimensions, but so that all the dimensionless numbers remain conserved. And we can superimpose basically simulation and experiment one-to-one. And now with these very nice results, we wanted to go ahead and say, well, let's do more adhesion and also not have one static picture, but perhaps movies. And so we went ahead with a more typical surface that came from experiments. So now simulation is again the second twin. And we acquired digital twins from the experiment, had an optical image of the surface, a total internal reflection image of the contact. And then what happened not only in this collaboration within Saarbrücken, but also with others, is that when we dumped the data into our calculations, when you visualize where you have contact, where you visualize where you have stress, you tend to see a lot of artifacts. And here you would basically recognize where the image was stitched together. And I think the stitching modules that are used might be improved so that we can have a more rigorous comparison between simulation and experiment. Some of the details you would see, some scratch marks in the contact topography are mimicked quite well, but of course, these things are highly annoying. So we went ahead, took a bit coarser structures and run additional detailed comparisons of rough contacts. So we would probe adhesion under tensile loads. And when we started writing up what we did, we actually noticed that the only journals we could submit our studies to would need to have complete failure in the title. So we had a really hard time to produce movies of structures that come from experiment and to really have a one-to-one match with reality. So whenever you have mistakes and discrepancies that you can't identify, what you do is you go to a simple reference. And you may argue the simple reference is a bit more complicated because now we have triplets. We have reality, we have a numerical model, and we have an analytical solution. That's always a very nice reference. And the type of reference that we took is a standard experiment, namely a flat punch experiment where basically we know that the flat punch has a really smooth surface, so a few nanometers roughness. We know the velocity, we know the indentation radius. And the nice thing about the flat punch experiment is that there are analytical solutions, in particular for the tensile force or compressive force, which is basically excuse me, a linear function of the displacement because the contact area doesn't change, right? So this is why, at least within linear response theory, you get this linear relationship and you can read off the value of E star from experiment. Our experimental collaborators used very, very small velocities in the range of micrometers per second. So the strain rates are 0.1 millihertz. Relaxation time of PDMS is fairly slow. So by all means, we should be quasi-static. And then we can run our favorite boundary value method, which is Wien's function molecular dynamics, where you basically only have to simulate the top layer, but you get the full elastic response from the bulk. And so when we compared the force displacement relation, we would see that, yes, of course, we can reproduce the slope. We can use that as an input parameter. We can set basically the pull force here. And you do see what you would expect from the analytical solution, where basically the tensile force increases linearly with the displacement, the contact breaks, you get a discontinuous tensile load. And in experiment, there was a bit of a curvature. So we agonized about, and again, the E modulus at 1 hertz is pretty much the static modulus. The rate is 10 to the minus 4 hertz, so nothing exciting here. So the only thing we could come up with was to say, well, perhaps there is a bit of a shape. And in fact, when we highly resolve the shape of the indenture, we do see a bit of a shape to the indenture. And with this shape, we can produce a force displacement curve that looks like the experiment. But when we actually put in the experimental result on top of that, we would see that, yes, the outcome looks alike, but the reason is wrong. So here we have a case of a doppelganger. And I think we have to be careful when we run simulations that we don't claim doppelgangers to be identical twins. So the other word for doppelganger in English is lookalike. Yeah, so we did go back and said, well, perhaps after all, we missed something on adhesion, and perhaps 2 or 3 of the next speakers already know why we failed. It took us a bit longer to figure this out. So we said, well, let's put in a viscoelastic model, a very simple model, 3-element viscoelastic model. I think Bunikura was the first one I know of who put it in a boundary value method in Fourier space. Lucia Nicola implemented it for Green's function molecular dynamics, and now we have our own implementation. And so the equation of motion for a surface undulation looks like that. You simply see the only time scale coming in is the time scale of the relaxation of the PDMS. And here on the right-hand side of the equation, so you can map that model onto this differential equation. Here the time scale even gets reduced because the static contact modulus is much lower than the high frequency modulus. And so we would think there are no viscoelastic effects, but we actually first missed something very important. And so here you see the movies, what happens when we put in the viscoelasticity using parameters that we hope are not completely unreasonable. And what you get to see is that basically when we move quasi-statically without viscoelasticity, the contact breaks at this point. And what happens is that it takes a very large force to propagate the crack. So in reality, you have crack propagation when the contact breaks. And in viscoelastic systems, where the difference between high and small frequency modulus is very different, there is a whole lot of dissipation that is going on in here that we need to capture. So I would like to discuss this a bit for a moving crack line, which we didn't do for a flat punch indenture. I had a collaboration with Wu Persson. We just got the work rejected from FISREF letters, which may actually be a sign for this to be a good paper. This is dimensionless, so you could argue that this is a cylinder in static contact. And when we pull up a cylinder, what happens is you get 2 moving crack lines. So basically, let's interpret the breaking of a contact as propagating crack lines. And this crack moves down. So essentially, when you move this up, this crack moves to the left. And now when you put your thought into a moving frame, where basically this crack is moving to the left, you can take that as a picture. But when you have a camera that moves along, you would basically see that from one image to the next, that's the normal distance that a grid point has to pass. And so in a moving crack line, even if the center of mass moves very slowly, you have some atoms that move very, very quickly. And basically what happens is when a point within, let's say, a time delta t has to move down a certain distance, that distance basically diverges in the continuum theory. So this profile would be a square root. This would be a square root in continuum theory. When you take the derivative of that, you get the velocity under quasi-static motion, and you basically get diverging velocities at the opening of a crack tip. And you are just at a point where you can ask the question, is the trajectory of these atoms continuous or discontinuous? So the old story, I mean, people who've known me for 20 years know I like to bring this up here and there, is the big question, do the grid points move in a continuous fashion or in a discontinuous fashion? Because depending on that, if you move in a continuous fashion at very small velocities, anything is basically becomes linear response. And whenever you are in linear response, your dissipative force, so your friction force, is going to scale linearly in the velocity. And when you have instabilities that you may have encountered in the Prandtl model or in the Tomlinson model, then each time you advance the crack tip by 1 grid point, you get a pop, and this pop dissipates the same amount of energy no matter how slowly you move. So you get a friction force, which, like Coulomb friction, is very, very insensitive to the velocity and perhaps has corrections linear in velocity. So now, of course, as you approach a critical point, you can switch between the two in the simulations by changing the range of the adhesion and or by changing the discretization of your manifold. So let's assume we keep the size of our atoms fixed and we simply have another counterbody having shorter range adhesion. What happens, like mathematically speaking, there's only continuous and discontinuous. But what happens if you sit precisely at the point between continuous and discontinuous? So on the left, on the blue side, you get a friction law that is linear in velocity and disappears. And here you have a different constitutive model. And in between, you get a so-called critical point where you get small velocity friction, where you get a power law. You're neither this nor that. They're exactly 1 point in between, separating blue from red, and so separating continuous from discontinuous. And this point is neither continuous nor discontinuous. So what's the bad news about this is that the velocity, the friction, the dissipative friction, so at small velocities, is determined at small scales because you have to know what happens when you zoom into the contact. And that basically means that continuum mechanics for a propagating crack point is a critical point. And that means that you're very susceptible to small details. And just to show how the motion is different for continuous and discontinuous motion, I'm showing here a movie of a propagating crack front, where you see here each point actually always has one well-defined stable position, which it tries to reach. And here, when you're discontinuous, a minimum that was stable in the past all of a sudden becomes unstable, and you have a discontinuous change to a new position, which then basically leads to a different law, and which means you get much, much greater adhesion. And actually, in these two movies, everything was the same from a continuum mechanics perspective. The only difference is, how do I terminate continuum mechanics at the small scale? So this problem also comes up when we talk about static problems. And now I'm going to switch gears a little bit to a different problem, which is experiments of flat punch contact mechanics of confined layers. So these are done when adhesives are evaluated. So you have a solid foundation, you get a thin layer of an elastomer, and that is being indented with a rigid punch. So things become interesting when the radius or the diameter of the rigid punch is no longer large compared to the height of the foundation. So in the limit where this foundation is very large, so when yellow is a lot higher than blue is broad, you have the classical flat punch indenter on a semi-infinite foundation. Now, one property in this setup that is interesting to study is the so-called effective modulus. So the effective modulus basically is the ratio of the mean stress in the contact divided by the relative height change in the elastomer within this contact. And that has an interesting behavior. If you plot the effective modulus, I mean, this has been done 20 years ago, we didn't invent this. If you plot the effective modulus of a flat punch as a function of the ratio of height over the radius, you see a scaling behavior for large film heights that you can get out of the regular flat punch solution on a semi-infinite foundation. So it decreases, and then at very high confinement, so high confinement means small elastomer heights, you get a minimum if your elastomer is close to ideally incompressible. So when you have an ideally incompressible solid, you actually get a power law that scales with the inverse power of h. And basically, this is due to the fact that if you have one sticking condition, at least one sticking condition, when you start squeezing down the indenter, you are starting to see a little bit of the bulk modulus, right? And when you start to see the bulk modulus for an elastomer, you start to see something that is very, very stiff. And this is why you get a relative minimum here. And if you're running out of questions, you can ask me, what is the meaning of these drawn lines? So one of the interesting things in this plot is that when h over a is small and the Poisson ratio, so here we see curves for different Poisson ratios. So when the Poisson ratio starts to be greater than, let's say, 0.4 or 0.45, you start to see very small minima. And in this range, you actually start to get stable crack propagation when you recede this guy. So when you recede the indenter. And when h over a becomes greater than 0.45, you start to see elastic instabilities. And they arise once you start having cracks. It's cheaper to put the elastic undulation or the non-contact onto wavelengths that are roughly have the same wavelength as the elastomer is high. So what you get under a receding contact, this is the curve you saw before, you basically see a spontaneous splitting of the contact into different domains. So here we have the maximum, and all of a sudden, boom, you start to get to see an elastic instability, and which is a means for the system to reduce the elastic energy. Now, what is intriguing about this instability is that depending on the level of detail that we put into our simulation, or the way how we basically truncate continuum theory, we get completely different patterns of the non-contact. So what you just saw in the movie was basically a cross-section across one such layer, where yellow is contact and blue is non-contact. So here you see the stress. And so in each row here, we have the exact identical continuum description, but we do some details different in the way how we solve continuum mechanics. And basically what you would see here to the left is when we do a very fine discretization and we have no lattice trapping. So lattice trapping is when you get the instabilities jump into contact of out of contact of individual grid points. And we sometimes see basically the spherical symmetry of the problem. Here, this is for a Poisson ratio 0.48. So we're not yet really ideally compressible. When we go a bit closer to being incompressible, we are seeing patterns that actually reflect the discretization of the problem. So we have to discretize our problem, and we discretize it into squares. So what you still see here is basically the symmetry of our discretization and or the symmetry of the periodic boundary conditions that we apply. What's more important actually is the symmetry of the discretization. So this whole thing was discretized into 1000 by 1000 points or 2K by 2K. I don't remember. Now, when we switch on a little bit of temperature, and this temperature is tiny, it would be roughly in the Kelvin regime, we see a very big symmetry breaking. So all of a sudden, these nice patterns break up and start to make these shapes. And if we take out the temperature again, but induce lattice trapping, we see a much greater violation from circular symmetry. And so it really matters how we truncate continuum mechanics, which I believe is an important message to know. And just to show that these things relate to reality, I show you some experimental pictures of similar contacts where you would see that what we do is not entirely esoterical. Then quickly going back to adhesion. So we were encouraged again, saying what we do is not completely meaningless, but we still have to improve on things in terms of reproducibility. And what we started doing is we print surfaces. We first create a digital model, which then goes into print. And you can see the plateaus from the 3D printer, which then we actually dump into our digital twin. And then we want to look at the effect of roughness on the adhesive forces. And what you see here is you have roughness on a single wavelength. And this single wavelength, depending on whether you call these maxima or minima, you get a hexagonal lattice or you get a triangular lattice touching. And so here we go into contact. You very quickly, when the hexagonal lattice is making contact, you see a very quick jump into contact where it's very hard just to keep the maxima in contact. You immediately form the ridges here, and qualitatively, this movie, perhaps I have to switch on the pen. Let's say, I don't want to reset. No, okay, so with a laser pointer, I cannot switch on that movie. I apologize. So I cannot show the experimental movie, which looks similar. Oh no, now it's running. So you also see the formation and retraction. You see similar dynamics. Now, if you compare the tensile force, so now we get the movie straightened out. And if we compare basically the tensile force as a function of the displacement, I think we can claim a lot of similarity with the experiment, but there's still some features where I wonder how we can better model the breakup here. But we do see a similar jump into contact instability as an experiment and a similar retraction. And for the triangular lattice, where we have the same spectrum, but surfaces, so heights and minima inverted, we also see similarity, but not to the way that we can really declare victory. So we are still thinking about how we can get this bump so that what we produce really is a twin. So I think I could show that we are on a good path to be quantitative. One of the big challenges is to be short-range adhesive, also because that adhesion, basically the short-range adhesion dominates the dissipation at small distances, so that we get the frictional effects modeled realistically. Putting in more realistic rheology is a matter of putting in the time. And I think one thing I would like to know is if the origin of adhesive hysteresis that we often see is due to viscoelasticity or due to multi-stability in contacts. And with that, I would like to thank you for your attention.